All right, we've done some examples in 2 dimensions. Let's look at an example in 3 dimensions of linear combination in a span. So let me tell you 3 vectors. Here's one. V1 is the vector 4, 1, -1. V2 is the vector 2, 3, 1. And V3 is the vector 1, 4, 2. And I'll give you a 4th vector, W, which is -1, 1, 1. Okay, and so suppose we wanted to ask, is W a linear combination of the V's? Okay, as we've seen, that's really asking the question, can we find x1, x2, x3 scalars, so those are real numbers, such that x1 v1 plus x2 v2 plus x3 v3 equals W. And if we try that, let's see, so that, as we know, will turn into the augmented matrix, basically. So we're going to take the columns, or the vectors, and make them into the columns of a matrix. Here's the augmented column, and I'll put W there. And we row reduce, and I'm not going to do these by hand anymore. You should do it or figure out how to make a computer system do it. I may make a video about how to make computers do this stuff later. But if you do that, I claim that you get the following. If we go all the way down to reduced echelon form, we're going to have a -1/2 here, a 3/2 here, a 0, and then -1/2 and 1/2, 0. Okay, so this is, take a moment and think, is this consistent or inconsistent? It's consistent, right? There's a row of zeros, but there's no 0 equals non-zero problem there. So, so this is consistent. And so the answer is yes. The answer to the question up here is yes. If we wanted to really write down, you know, we could sort of think about writing these equations out very explicitly, or we could just sort of say, well, okay, look, this is a free variable, clearly. X3 is a free variable. So it could be 0. If we just wanted to actually get an answer, like find W as a linear combination, the simplest thing to do is set x3 equal to 0. And if we do that, then that means x1 is -1/2 and x2 is 1/2, right? Basically, these become irrelevant when the x3 is set to 0, and then you just get x1 equals -1/2 and x2 equals 1/2, right? And so that therefore means that W is -1/2 V1 plus 1/2 V2. So that's nice. And in fact, I would, it's very satisfying to check. So I would actually go up here and write scale this by -1/2, scale this by 1/2, add them together, and you should get this. It's a nice check. So I would do that. I would stop, pause, check. Okay, then I want to talk a little bit about, there's something sort of interesting here though, because V3 didn't come into this at all. And in fact, this means something about the relationship between V1, V2, and V3. So I want to notice, if you just look at the coefficient matrix and forget the augmented column, you could almost think about, so forget this, you could almost think about making this the augmented, making the third column the augmented column in a 3x3 matrix, right? So if you just take, by the way, I should probably mention you know, it's nice to write sort of things this way, to note that the columns are of the original matrix are V1, V2, V3, and W. So if we just write down the matrix whose columns are V1, V2, and V3, like this, sometimes we'll write things this way. You've probably seen this in the book already. Then what the computation above says is that you would actually end up with this negative 1/2, 3/2, 0. Maybe I'll do it like that. And then that actually means you can also, just like we did up here, there's no free variable anymore, but we could sort of say, okay, in fact, we could say W, this is really about asking, maybe I should say it this way. This is really asking X1, V1. Oh, what am I doing? I'm sorry. I wrote W here, or I meant to write V3. Sorry about that. V3. Okay. So this is really asking, is V3 a linear combination of V1 and V2? And the answer is yes, because this is still consistent. And so this means that V3 is in fact negative 1/2 V1 plus 3/2 V2. And again, this is something you should check. It's sort of satisfying to see this. V3 is actually itself a linear combination of V1 and V2. And that means interesting things, right? So if you think about it, V1 and V2 definitely point in different directions in space. One's not a multiple of the other. But V3 is some sort of linear combination of V1 and V2. So I actually have a visualization of this. Let me see if I can change the share. Okay, so here is a picture of all of these vectors. So the three blue vectors are V1, V2, and V3. The gray vector is W. And then I plotted I, or actually it's 4I to be precise, the red vector, just to sort of show you another vector. So that's just the vector in the positive X direction. And here's the thing. So you can drag this around. This is within Mathematica. It's kind of nice. You can see somehow that the four vectors, except the red one, are all related to each other, right? They kind of look like they live on the same plane, maybe. Hopefully you can see this as I'm dragging it around. And it's not too choppy, but yeah, like I is sticking out, but then the four of these kind of look like they're in the same plane, which makes sense if V3 and W are both linear combinations of V1 and V2. If I scroll down a little bit, I actually have a picture with the plane also. So here's the plane. You can see the three blue vectors, which are V1, V2, V3, and W, the gray vector, all live in this plane. And so in fact, this really what we're looking at is the span of V1, V2, and V3. And then I, the I vector, is actually sticking out of the plane and isn't part of it. So I is not in the span. And we could see that if we tried to row reduce with I as the augmented column, we would get an inconsistent system. Let me try to switch back to the iPad now. See if this will work. Okay, so here we're back. So this now I want to talk about the span. So the span of V1, V2, V3 is actually not all of R3. We just saw that you basically can only get a plane's worth of stuff because really V3 is not extra. V1 and V2 are enough to span this plane, and then V3 is in the same plane. So this is a plane in 3D space. In fact, you could also say things like the fact that V3 turns out to be redundant because it's a linear combination of V1 and V2. You could also say something like this equals just the span of V1 and V2. You don't actually need V3. And also we saw that W, maybe just to write a mathematical statement, we saw that W was in the span of V1 and V2. But in the picture, I was not, I hat, maybe I should use I hat, was not in the span of V1 and V2. Okay. And you could do that. You could actually, you know, put the I vector here and row reduce, and I claim you would get an inconsistency right there. Okay. Maybe one last question I could ask is which plane? You know, if this is a plane, we saw the plane in that picture, which plane? Can we say, can we get an equation for that plane? We know how to write, if you took multivariable, you know how to write down equations of planes in space. And in fact, there is a way to do it. You can sort of do the following. You can actually take the original equation, the original matrix, sorry, 4, 1, minus 1, 2, 3, 1, 1, well, I'll go ahead and put the V3 in there, even though we sort of don't really need it. And then you could augment with sort of an arbitrary Y1, Y2, Y3. And you could row reduce. I'm actually just going to reduce it to echelon form, not even reduced echelon form. And if you do that, I claim you get the following. You get 1, 0, 0, you get 3, 1, 0 is the second column, 4, 3 halves. It's the same steps that you would have done to row reduce. But then what happens in the augmented column, this is just Y2. This turns out to be minus 1/10 Y1 plus 2/5 Y2. You should probably check this. But then the last one is sort of what's interesting. I get 2/5 Y1 minus 3/5 Y2 plus Y3. And now if we look at this bottom row, well, in order for this to be inconsistent, this quantity right here better be 0, right? And really what that means is that we need, we need, well, maybe I should say it this way. In order for Y1, Y2, Y3, let's actually give that vector a name. Let's call it Y, the vector Y. This is V1, V2, V3. In order for Y to be in the span of V1, V2, and V3, or just V1 and V2, it doesn't really matter. We need this 2/5 Y1 minus 3/5 Y2 plus Y3 to equal 0. Or you could scale or, you know, multiply by 5 everywhere to clear denominators. So you could also say 2Y1 minus 3Y2 plus 5Y3 equals 0. And this is the plane. So this is the span. This plane is the span of, this is a plane in space. You know, if I think of the axes being Y1, Y2, Y3, this plane is the span of V1, V2, and V3. In some sense, right? And again, another thing to check, I would say check. It's really, again, very satisfying that V1, V2, V3, W all satisfy this equation. That if you take the components of V1 that, you know, if you know, I just go back up to V1 right here, right? If I do twice 4, I get 8 minus 3. So 2 times 4 here, put in 1 here, and put in -1 here. 8 minus 3, and then that's minus 5, and you actually do get 0. And so that's awesome. So that satisfies it. And I would say check each of these also and W. And then you really do see the equation of the plane, which is nice. So that's a way to find an equation of the plane. Yeah. So I think we sort of analyzed this completely. So, all right. I will say some more general things in the next video, but for now I will stop.